Greetings, fellow mathematicians. We're going to take a look at another example of a second order ODE with constant coefficients, but this one, it's going to be a little complex. So let's get right to it. As always, start with your ODE. We know we're going to get exponential functions of the form y equals e to the rx as our solution. So calculate your first and second derivatives. I always like to go through this with my students just so they don't miss any factors. And you can shortcut carrying along the exponential function since we're going to factor it out anyway, since it's contained in every term. And we should get as our characteristic equation r squared plus 2r plus 5 equals 0. And I'm looking at that one, and I don't think that one easily factors. So what can we do with that? Quadratic formula. So let's go ahead and crank that out. We have r squared plus 2r plus 5 equals 0. And just to identify your coefficients for the quadratic formula, our value of a is 1, value of b is 2, and value of c is 5. The only difference is instead of getting x as your solution, we're getting r as our solution here. So the quadratic formula should give us r equals negative b, so negative 2, plus or minus b squared, and then minus 4ac. It looks like that's going to be minus 20, and that is all over 2a. All right, notice we're going to get a negative inside that square root, so that's going to give us negative 16. And if you take your square root of that, introducing I, we can write square root of negative 16 as 4i. And then that's all over 2. And notice, since each term in the numerator contains a factor of 2, we can divide the 2 in the denominator into that, giving us our complex solutions, negative 1 plus or minus 2i. All right, from here, these are our values for r. So we get negative 1 plus or minus 2i. And we want to identify the real part and the imaginary part. And this is for our general form of the solution in the complex solution case. So we have the real part as negative 1. And the imaginary part as 2. We just plug in a as negative 1 and b as 2. So it looks like what we get as our solution up to your two constants. We get c1 times e to the ax, where a is negative 1, times sine of bx, where b is 2. And then you have a similar term with the sine replaced with a cosine term. So plus c2 times e to the negative x times cosine of 2x. All right, now we have some work in front of us to solve for c1 and c2 using the initial conditions. And the work here is going to be involving the derivative. This involves product and chain rule, and so does that. So let's go ahead and get to a clean board, and we'll go ahead and solve for c1 and c2 directly from here. All right, let's go ahead and solve for the values of c1 and c2 using the initial conditions. This is going to be a little bit of work because in order to calculate y prime, notice we're going to have to apply the product and chain rules twice to each of those two terms. I'll take my time with my students in class when going through this, so let's do the same now. And for us, when we apply the product rule, we're going to think of the constant times exponential as our f, trig function as the g. So let's calculate the derivative. So we'll differentiate the first term. We'll get a negative c1 e to the negative x, and then times the second function. And now we add to that the first function times the derivative of the second, and that's where the chain rule comes in again, giving us a factor of 2. So we'll write that as plus 2 c1 e to the negative x times cosine of 2x. All right, these two terms come from differentiating the first term there. We're going to apply product and chain rules again to differentiating the term involving cosine up here. So let's go ahead and do that. Instead of putting the work to the side, let me put it right below here. So again, differentiate the first function. We'll get a negative c2 e to the negative x times cosine of 2x. And now we add to that the first function times the derivative of the second, but we know the derivative of cosine is negative sine. So there's actually going to be a negative there, and the chain rule gives us another factor of 2. So we'll write that as minus 2 c2 e to the negative x times sine of 2x. Now this looks kind of like a mess since there's a lot of stuff floating around, but we can combine some of these quantities together. We have two terms, exponentials times sine and exponentials times cosine. So let's identify your exponential times sine terms. That's right here and right at the end. So we're going to factor out the exponential times sine, and we'll write y prime as, in parentheses, the coefficients, negative c1. And then what's your other coefficient? Minus 2c2. And that's times e to the negative x times sine of 2x. And we have similar terms left, but exponential times cosines, and that should be this one along with that one. So again, we'll factor out the exponential cosine. And it looks like our coefficients, we have 2c1 and then minus c2. And that's times e to the negative x times cosine of 2x. All right, that is most of the work. Now we can very easily plug in our initial conditions where x is 0, and notice we have sine and cosine, and we have two very nice values that we'll be making use of. We're going to end up with sine of 0 and cosine of 0. Now hopefully you recall your basic trig. What you should find, cosine of 0 is 1. Sine of 0 is 0. And that's going to give us a very quick way to plug in x is 0. Half the terms here in y and y prime just disappear due to the sine term evaluating to 0. So let's start with the function initial condition. So we're going to plug in for the function initial condition, x is 0 and y is 2. And we're going to keep in mind that sine of 0 is 0, cosine of 0 is 1. So if we plug that in, we get our y. That comes out to 2. And what are we left with? When we plug in x is 0, We get sine of 0, so that's gone. And what we're left with, cosine of 0 and e to the 0, which are both 1. So on the right side here, we're just left with C2, the coefficient of the cosine term. So that's done. That tells us that C2 has the value 2. And we're going to plug in the derivative initial condition to this mess of y prime. So our derivative initial condition is y prime of 0 equals 1. So again, we're plugging in x as 0, y prime as 1. And again, we know the sine term is going to evaluate to 0. So we can kind of cut out some of the work here. Y prime is going to become 1. We know the sine term here, that's just going to evaluate to 0. And what's left is your cosine of 0 term, which is 1. And again, e to the 0 is 1. So we're just going to be left with, on the right side, 2c1 minus c2. Now we already know the value of c2, so we can plug that in. And it looks like what we're going to be left with is the simple equation 1 equals 2c1 minus 2. And you're probably okay with the basic math from here. Add 2 and then divide by 2. Looks like what we should get there is c1 as 3/2. And that's it. Most of the work that we went through here was implementing the product and chain rules twice. And that just goes along with the case of complex solutions. So if we plug in our values of c1 and c2, we can get our solution here. And if we write that down, we have c1, which is 3/2. So we get 3 over 2 e to the negative x times sine of 2x. And our value for c2, we found that all the way on the other side is 2. So plus 2 e to the negative x cosine of 2x. And there we go. I hope you enjoyed the video. If you did, support the channel. Make sure to like and subscribe. That way we can keep going through more awesome content.